All right, welcome to this lesson. In this lesson, we're going to go over bend. Oh, switch. Go to white here. So bend, length, calculations. Okay, so I'll just draw an example here. So for sheet metal, you have a straight section with a radius section and then a straight section. Okay, so here's the straight section, the radius section, and then the other straight section. And these bends occur at some sort of angle. That angle there. So for any formed piece of sheet metal, you need to state on the drawing the angle of the bend, the inside radius, and the thickness of the material. All right. But as you can see, on the outside radius, the material is longer than the material on the inside radius. So if you were to flatten this out, what would be the length of this radius section? So if we analyze this piece here, like this, oops, I don't like that. There we go. So if we just take a look at this piece, let's see what's going on in it. We're just magnifying this piece here. So if we look at it on the outside, it's definitely in tension. So the forces within the material are going like that. And on the inside, you have compression, like that. So if the outside is pulling or in tension and the inside is in compression, at some point along the thickness here, there's going to be a neutral axis. And at the neutral axis, there is no compression or tension, which means that the material is the original length. It is neither being stretched or compressed. So if you were to flatten this curved section out, and you look at the neutral axis, so this is the neutral axis. It has the same length as the neutral axis when it is unbent or original shape. Okay, so now if we know that this neutral axis is the same length, then we can take a look, we can calculate the length of this bent shape based on the geometry of the bent shape here. So, and we do that by using the SOAR formula, as I call it. So S, which is arc length, is equal to the angle in radians times the radius. So this has some sort of radius. It has, so we'll draw that out. Maybe I'll use yellow here. So this has some sort of radius, and it is at some sort of angle. So r and the angle in radians. Radius. So that's radius, not the inside radius, not the outside radius, but the radius at the neutral angle. And so you may ask yourself, okay, well, how do I know where the neutral axis is? Well, the neutral axis, if the material hasn't deformed or has very large radius relative to the thickness of the material, is right in the middle. But if you've deformed the material, that neutral axis moves towards the radius, the inside radius. So to calculate the inside radius, or sorry, the radius, here we use three basic rules. So, three basic rules. So I'll redraw this shape here. Like that. So there's the straight section, the curved section, which is the bend, and another straight section. So we have a inside radius. There's some sort of angle that this part has been bent to. And there is a neutral axis, which I'll draw in correspondence to the three basic rules. And of course, the material has a thickness T. Okay, so maybe in purple here, I'll draw the first rule. So if the inside radius, Ri, is less than the thickness, so less than T, the bend length, or the arc length, is equal to, so T over 4, so the thickness over the 4, plus the inside radius times the angle. All right, so this angle here so the angle bend is equal to this angle here, angle bend, the bend angle. So those are equal, and it has a midpoint like this. So if you were to measure this distance and that distance and this distance and that distance, they're also the same. So this distance here is equal to this distance there, if you go directly to the center of this bend. We'll use that information in another video. Okay, so if we look at this formula here, it's really the arc length, which is the bend length, is equal to the angle in radians, so that's the bend angle, times the radius. Now the inside radius goes to the material, and the neutral axis exists at just a quarter of the thickness below the inside radius. All right, so I'll use we'll go, that's half, this is about a quarter here. So that is where the inside radius is when when the inside radius is less than the thickness. Maybe I'll use orange now. So if the inside radius is greater than or equal to 1t, one thickness, or less than or equal to 2 thicknesses, BL, the bend length, is equal to T over 3 plus RI times the angle of the bend. Maybe I should use the same notation here. So that's the angle of the bend. There you go. Okay. And so if I draw this, 1/3 of the material is about here. So this is where the neutral axis is. If the inside radius is between 1 and 2 thicknesses. If the inside radius is between 1 and 2 thickness of the material. So we have, what about a big bend? It's got a big radius on it. So that rule, maybe I'll draw in green here. So if Ri is greater than 2 thicknesses, material thicknesses, BL, or bend length, is equal to T over 2 plus the inside radius times the bend angle. So that would occur right at the halfway mark. All right, so really we're adding, if you look at this formula, we're adding the inside radius, and we're then adding that to the distance to the neutral axis, which occurs at some point of the thickness. So this would be the maximum. Your bend length approaches your Ri as it gets tighter, and then it approaches the thickness divided by 2. So it never goes above divided by 2. It's just that's it. So this is kind of like if you bend something and there's no deformation at all, or permanent deformation, I should say, your neutral axis is still in the middle of the part, and so it approaches that value when your inside radius is 2 thicknesses. Okay, so things that help in this, and one thing that I should note here is that all of these angles are in radians. So you might not be comfortable working in radians, but really it's truly easy if you, I shouldn't say it's easy. If you understand the unit circle, it becomes very you feel more comfortable working with it. So I'm just going to take the rest of the video to go over conversion of radians to degrees. So if you're comfortable with that, you can pause the video here, but if you want a refresher or you're uncertain, keep tuned in here. So let's first draw the unit circle. Okay, so the unit circle is a big circle like this, and on it are degrees and different angles. So circles have a center. So at 0 radians equals 0 degrees. And there are no units known or like symbols for radians. Sometimes you'll see rad, but no symbol like degrees has. So at 180 degrees, this is just something you got to remember. You have pi rads. So at 360 degrees, shares the same point as 0 degrees, you have 2 pi. So the circumference, there are 2 pi radians per one whole circle. So if pi is 180, what's 90? 90 degrees. It's half of pi. So pi divided by 2. And so if this is a half of a pi, then this is also a half of a pi, and you just add them together. So 1 pi over 2, 2 pi over 2. 2 divided by 2 is 1, so you're just left with the pi. So 2 pi over 2. 3 pi over 2 brings us to this point. So that's 3 pi over 2. And so that equals 90 plus 180, which is 270 degrees. And so if you wanted to know what 45 degrees is, it's just half of pi over 2. So pi divided by 2, which is pi over 4. And so if you want to know this angle here, you have 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. And so that would be 90 plus 45, which is 135 degrees. 45 plus 135 equals 180. 180 plus 45 is 225. 225 plus 45 is equal to 270. 270 plus 45 is 315 degrees. So you keep going around. So you could figure out 30 degrees. So what's 30 degrees? 30 degrees is pi divided by 2 divided by 3. There's 330 degrees in a 90-degree angle. So pi over 2 divided by 30, or sorry, divided by 3 is pi over 6. And so you could figure out all of those ones, and it just keeps working like that. So I just brought up these angles because they're very common angles and easy angles to work with. So if you want to do more complex angles, like maybe you want to know what 32 degrees is. So what is that in radians? That's the big question. It works out like this. So if you want to know the degrees, so degree is equal to, you want to know what sorry, you want to know what how many radians 32 degrees is. All right, so it's going to equal to your degree value. So x degrees times pi over 180. So equal x radians equals. So you would insert the 32 in here, and you'd multiply by pi over 180 because there's 180 degrees per pi. So if you want to know how many degrees from radians, you would just flip this around. So, or you could isolate degrees. So let's isolate degrees. So x rad is equal to x degrees times pi over 180. So I'm going to isolate degrees in this. So I'll divide by pi, and I'll divide by pi. So the pi's cancel, or become 1 on this side. And whatever I do to this side, I have to do to this side to make them equal. So by that logic, I'll just multiply this side by 180 and multiply this side by 180. And so the 180 degrees cancels on this side. So if I rewrite this out nicely, x degrees is equal to x rad times 180 degrees over pi. So if you wanted to know, make this equal to 90, I'll just show you very quickly. If you wanted to calculate this, so pi over 2 radians times 180 over pi equals x degrees. So the pi's cancel, and you're left with 180 divided by 2, which equals 90 degrees. So these are the formulas that you should know by heart. Maybe your calculator does this for you, but this is something you should really strive to understand. Make your engineering life just better in all ways, just totally better if you understand the unit circle. All right, so that kind of goes over the unit circle here. You have your 3 basic rules for determining your bend length, so BL, and the BL formula comes from the SOAR angle, which is just an arc length calculation. And that will help you find any degree angle part. So I hope you enjoyed. Let me know if you have any questions, and we'll see you in the next video where I will be going over figuring out bend height for anything from 90 degrees to less than 90 degrees. All right, thank you.